In this video, we will be taking a look at the Laplance transformation of these examples. You can notice that all of these examples are consisting of e power at. This means we will be solving these examples using the shifting property. After that, we will move on to another important technique using the property of multiplying with the power of t's. Let's move on to the first example. Now, we are going to apply the shifting property onto this. This is a standard form of the shifting property, where e power at is given here, and sine of t is equal to f of t. So first, we will be taking the Laplace transform of f of t and replace every value of s with s minus a. After taking the Laplace transform of sine of bt, we will be replacing all the values of s with s minus a. So let's do that. This is our final answer. Similarly, in this example, f of t is equal to cos hyperbolic of bt. So we'll be taking the Laplace transform of f of t first and then apply the shifting property onto it. In this case, we can actually apply two properties here. We can apply the shifting property because there's e power at multiplying with f of t, or we can apply multiplication by t power n property because t power n is being multiplied with e power at. However, for now, we will only be applying the shifting property to solve this. And in future example, we will take a look at how to solve the same type of question using t power n multiplication property instead. So let's continue. We will first take the Laplace transform of f of t, which is t power n in this case, and then apply the shifting property. This is the final answer. In this case, where the cos of at is being multiplied with hyperbolic cosine of bt, we do not recall any shifting property or any standard Laplace transformation formula that applies as it is to this kind of multiplication. However, we already know that the formula for cos hyperbolic bt is equal to e power bt minus e power minus bt divided by 2. So we substitute this into our original equation here, and then break the term into two parts and solve each term individually. So let's do that. We have broken this expression into two terms, and now we are going to apply the shifting property on each term individually. We already know that the Laplace transform of cos is s divided by s squared plus a squared, and here S is going to be replaced with S minus B here and here. Similarly, for this one, we will take its Laplace transformation, S divided by S squared plus B squared, and replace every S with S plus B. This will be giving us our final answer. Take a look at these examples. In each of them, we will be carrying out the Laplace transform using the multiplication with t power n property. This property is also known with other names such as time domain power rule or time multiplication property, and even frequency differentiation property. This is going to be the standard formula which we'll be using. And here we will be doing minus 1 to the power of n, d power n divided by ds to the power of n, f of s, where f of s is the Laplace transformation of f of t. So let's start with our first example, t squared e power at. In this example, we can see that t power n is equal to t squared, and f of t is going to be e power at. We will first take the Laplace transform of f of t, and then using this formula, we will place it in f of s. So let's do that. Now applying the multiplication with t power n property. Now you can see that we will be taking the double derivative, and for this question, we will be applying the quotient rule, which is this. Taking the first derivative, now taking the second derivative, this leaves us with 2 s minus a. And this s minus a is going to cancel out, leaving s minus a cubed in the denominator. So the final answer is going to be, in this example, we will first find the Laplace transform of cos at, and then apply multiplication with t power n property. So let's do that. Applying the multiplication with t power n property. Taking the first derivative. Now taking the second derivative. S squared plus a squared and s squared plus a squared is common in both of these terms. So we will be taking s squared plus a squared common. We can simplify this expression by opening the brackets and getting the final answer. So let's continue. This is our final answer. We are asked to find the Laplace transform of this expression. However, we notice that none of the standard Laplace transform formulas we have studied so far apply here. So we will be simplifying this trigonometric function using the trigonometric identity first. We already know that sine A sine B is equal to 1/2 of cos A minus B minus cos of A plus B, where A minus B would mean 2t minus 3t. So A minus B equals to 2t minus 3t. That is equal to minus t. And cos of A plus B would mean 2t plus 3t. That is equal to 5t. So let's apply this identity here. Now we already know that cos of minus theta equals to cos of theta. This is because in the ASTC quadrant, it is found in the fourth quadrant where the cos is going to be positive. So let's rewrite this as cos of t. Now using the linearity property, we will be finding the Laplace transform of cos of t and cos of 5t separately. So the Laplace transform of cos of t is going to be s divided by s squared plus 1. And for cos of 5t, it's going to be s divided by s squared plus 25. Take a look at this question. We can solve this using two methods. First, using multiplication by t power n property, because t is being multiplied with f of t. Then we will solve it again using the shifting property because e power minus 4t is being multiplied with f of t. Now, using the first method, we can see that t power n and t power 1 is here. And so e power minus 4t sine of 3t becomes f of t. We will apply shifting property on this one. Now, applying the shifting property on this one, we can rewrite it as removing this and writing s approaches to s plus 4 outside the Laplance. Then we will find the Laplace transform of sine of 3t. So let's do that directly. Now applying multiplication with t power n property, we will be substituting f of s here, and the value of n is equal to 1. Simplifying it further, we can see that this becomes 0, and this is going to become minus 6 s plus 4. So writing the final answer. Now let's try to solve the same question using the shifting property. In this case, we will be treating t sine of 3t as f of t. So f of t becomes 3 sine of 3t. We will be taking its Laplance transform. Let's rearrange it and write it much more neatly. We will find the Laplance transform of this, and we will, instead of writing e power minus 40 here, we will be writing as s approaches to s plus 4 outside the Laplance. So let's rewrite it. Now we will be considering sine of 3t as g of t for our understanding, and we will be applying multiplication with t power n property because t is being multiplied here. So we will find the Laplace transform of g of t separately. Applying the t power n multiplication property here, this becomes now here you can see that we had written as s approaches to s plus 4. Similarly, we will also be writing here as s approaches to s plus 4, and here s approaches to s plus 4. So this term becomes 0, leaving us with this. So we will be writing our final answer like this. We will be replacing every s with s plus 4 here and here, giving us our final answer. This is our final answer we have achieved using the shifting property on the same question.